All right, buenas noches, tardes, dias, whatever it is that you end up listening this to. My name is Andy Vandy, and I made the terrible mistake of believing that we exist in a multivariate world and attempted to use NMS and CCA to analyze some data I have on shortleaf pine regeneration across a variety of vegetation gradients within oak woodland and savanna restoration. So hopefully I can present to you some useful information about the two statistical techniques, and we can explore it together. So to start, shortleaf pine has declined by greater than 50% since 1980. And this has occurred primarily in the eastern United States, and right here we've got Tennessee, which is greater than 60%. So this is definitely a regional issue and something of concern for us. And the cause has involved past logging, disease, and insect outbreaks, but more than anything is the suppression of fire. Shortleaf pine is a very fire-tolerant species. It's adapted to fire. It sprouts basally. It's one of the few pines to actually do so, which puts it at a competitive advantage to responding after a fire top kills a lot of the woody vegetation. It can overtop a lot of its competitors. But in the absence of fire, that ability is taken from it. This suppression of fire has really led to overstocking within remnant shortleaf stands that have resulted in quite a bit of damage and exacerbated insect outbreaks, including the $1 billion in economic loss from the last outbreak of the southern pine beetle. And also this loss of shortleaf pine components has led to detrimental impacts on endangered species and the high levels of biodiversity associated with shortleaf pine woodlands and savannas. So, restoration has been suggested as a possible solution. Simply restoring fire and the sparseness of canopies can really lead to healthy and sustainable shortleaf pine ecosystems, and included in that is adequate levels of regeneration of shortleaf pine. But how do we actually do that? There's been discussions concerning seasonality of prescribed fire. Growing season fire occurs when the majority of a tree's resources are above ground and therefore limits its ability to resprout in the following year greater than more traditionally used dormant season fire. So I explored this at Catoosa Wildlife Management Area, which had a dominant shortleaf pine component prior to that last outbreak in the southern pine beetle. And the levels of salvage harvesting led to the initiation of an oak woodland and savanna restoration project involving prescribed fire. And this led to the patchy promotion of shortleaf pine regeneration. So in patchy in that there's areas where there's quite a bit of it coming up, and I really wanted to explore what it is about these areas where shortleaf pine is popping up in relative to areas where it is not. So I had two 20-hectare replicates of 6 different treatments. This involved fall fire prior to leaf abscission, so in the late growing season, and spring fire, which was in the winter, prior to spring green up, and paired with woodland or savanna residual basal areas. And I also looked at it in advanced savannas, which were burned 7 times, and unmanaged controls. Within each of these areas, I collected data at 15 plots, as you can see represented by this diagram here. And within each of those plots, I collected overstory, midstory, and ground cover data. Just example, overstory, live basal area, percent oak in the overstory, canopy cover. Midstory was woody stem densities of a variety of size classes, and then ground cover variables like percent woody ground cover, percent grass, forb, fern, and native warm season grass density, a variety of variables that captured that gradient in vegetation. Also at those plots, I collected data on all shortleaf pine that occurred within these 3 meter radius subplots. That included height, root collar diameter, basal sprouts, the largest basal sprout diameter, mid-story crown class, and then a calculated density based on the number of stems occurring within those subplots. My overall objective was to determine how the presence and vigor of these shortleaf pine vary across these gradients in vegetation. So for my first analysis, I chose to go with NMS, which collapses multiple dimensions into relatively few just to be able to visualize patterns. It is very robust and well known and well used within community ecology because it has no assumptions concerning normality or linear relationships. All of the tests are conducted on the rank orders of distances between plots. So basically what you do is place all of your observations within this reduced dimensionality, and you're guessing at their positions, and then you're regressing predicted versus observed, and determining a stress and moving those in the direction of decreasing stress until you've achieved you've reduced stress below a certain threshold, typically recommended as 0.3. And here's a pictorial representation of that process. And for more information, I've provided a link here that is a good summary of NMS. So doing it in R, all of this can be done using the vegan package, and the specific function is meta MDS. I looked at diagnostics using the MVN package. I noticed that a few of my variables were not univariate normal, and I did not have multivariate normality. And when I plotted all my data, I saw quite a few good linear trends, but some others that were not, kind of clumped or various different distributions. So I think that NMS was a good choice to analyze this data. So in R, here I've already imported my data into R. The first step is to set a seed, so just pick a random number and to set that. As I said, meta MDS is the function we'll use, and there's everything that you can know about it. But really, all it involves is creating an equals for your ordination, listing your data, as well as the number of axes you would like it to spit out. So I'll run that. It did 20 random starts and calculated stress for each of those. And if I look at what's contained within that output, I can see all of the variety of different calls. And here are the axes scores for all of my plots listed there. I can do the same for each of those variables that I had. And if I plot the stress, you can see that we did a reasonably job of having that ordination distance match up with the observed dissimilarity, and we explained 92% of that variation. So there's a good stress plot. So when we plot this, you can see that we've got our variables in the red plus signs, and each plot represented by the circles, ordinated on 2 axes in space. So if I go into here, as you can see, this is the results that I've kind of cleaned up and made sure. And what's really apparent is that we've got a conglomeration of all my variables that kind of capture this transition to more herbaceous dominant understory within these woodlands and savannas. Over here, it's more closed canopy live basal area and percent litter, more typical of closed canopy oak forests, as well as a section that's very dominated by all of this woody mid-story growth. So kind of a younger savanna that has yet to had that woody component reduced through fire. when we plot the plot scores on that same axis in space, we can kind of see this conglomeration of the advanced, the ones that were burned 7 times, that have that herbaceous dominance kind of falling into the same area. Our controls are up in that more typical closed canopy oak forest area, and then most of our younger, only burned twice, are falling into that really dense woody understory vegetation area. And if we look at them individually, we can kind of see we never had shortleaf pine as indicated by a filled symbol within controls. Pretty much equal distribution throughout our advanced areas. Within those spring burns, the dormant season burning, a pretty kind of cluttered up towards that really dense mid-story area, whereas in comparison, the fall, these are the shortleaf pine are kind of more down and towards, headed towards where these advanced areas would be. So that was good, but I thought that perhaps canonical correspondence analysis would provide me some more information in its ability to constrain that ordination with explanatory variables. So the thing about CCA is that it assumes a unimodal distribution, so that shortleaf pine, variables are, peaking at some area along the vegetation gradients, uses chi-squared distances, and the axes are linear and orthogonal, and it's also widely used, the most widely used constrained ordination method. So how it works is ordination scores are fitted values from a multiple regression between explanatory variables and the ordination scores resulting from a correspondence analysis of the main matrix. And yes, that is very difficult to wrap your mind around, which is why up here I've provided some good reviews of what this process actually entails. But really it's just the constraining out using your explanatory variables. So I found this could potentially yield some interesting results in that I'm not interested in the variation in all of this vegetation overall, but just what about it explains shortleaf pine. So if I only use if I constrain it by variables concerning shortleaf pine vigor, I will only be looking at variation associated with those variables. So in R, we're going to use the vegan package again, and this time it's function CCA. We can run those multivariate normality packages, which is required for CCA, and we can talk about that more in the discussion. And I also found all of these different functions that can really delve into, which I did, but for the sake of time, I'm going to skip. So back to R. So if we look at here, I've imported the 2 data sets, my shortleaf pine vigor data set, which as you can see here has a variety of different variables for each of these shortleaf pine that we will constrain the ordination by. So here's the function. I've assigned a value to this CCA results that is constraining the variation vegetation by all of these shortleaf pine variables, plus the treatment that they're in, which certainly would explain where shortleaf occurs, and all of that. Those variables are coming from that data set, so that's listed there. So if I run that, then I can get a summary, and this will show you all of the important components that you need to know. Most importantly here, this is inertia, which is basically a representation of the total amount of variation in the data set, and that our constraining variables explained 0.1 of about 0.3.5 or 0.35, which was around 30%, which is not a lot, but again, I'm not really concerned about everything, just what I can, what is impacting shortleaf pine. So if we come down here, this these axes show that the first two axes, jump up to about 22 of that 30%, and all of these axes are adding about 1 to 2%. So it is appropriate to look at just the first two axes of the CCA, and that cumulatively they explain 80% of that 30% that was explained by the short-leaf variables. So here I've got my scores for all those variables on those two axes, and then I've got my plot scores, which are all contained in that results, and the biplot scores, which are just these vectors along in these axes of all of the shortleaf pine variables. Also, because I had a factor level variable concerning my treatments, I've got these centroids, so basically where the average position is within this space of advanced, controls, fall savannas, spring savannas, etc. So go back up here and we will plot this NMS, or CCA, and here you can see that we have successfully constrained the data by these shortleaf pine variables and kind of stuck a lot of this up here. And I'm going to go to my cleaned up version of these plots in PowerPoint. So here's that all cleaned up. We've got that, most of this shortleaf pine variables that explain its vigor and robustness are going out right in this direction, which, as you can see, is very similarly all of those metrics of herbaceous understories. And out here we've got all of that, more typical closed canopy oak forest variables, and a section of more dense mid-story. And it's interesting to note that basal sprouting and the density is kind of going up in this direction, which are those areas that are dominated by woody vegetation. So if we look at the plots, you can see that these centroids come out to kind of showing that controls are over here, whereas the woodland treatments are kind of are in this position, as well as, and then the fall savannas, spring savannas, and the advanced areas are falling right down here, all very similarly together. And also these filled symbols are areas that had shortleaf pine, and you can see that we've constrained them all to be right there. So all the variation in that data has been constrained, and now we're looking at really where is this position and what's related to that in relation to our data. So in conclusion, it seems that CCA resulted just achieved my objectives much better than NMS in that those ordinated plots, it ordinated the plots together that contain shortleaf pine, and resulted in greater differentiation of treatments and the vegetation gradients. I think that it was more easily interpretable, but however, I do have concerns about the assumptions that are key to running CCA, and that both that unimodality of the response variables and then also the linearity that's involved in parsing out those trends. I did have this classic U-shape in my response, which some authors have suggested is this edge effect, where you've got less variation on the edges and then more variation in the middle. So my edges would be dominated by grass versus dominated by overstory, a thick overstory, and I think that kind of warrants some concern, and probably could use some transformation or some sorting out of variables that don't fit those trends. So that's directions for the future that I would consider as I move forward with these analysis. But if those assumptions are addressed, I really think that CCA could be more of what I want in terms of answering this question and looking at where the patterns in shortleaf pine and what it is and the vegetation is associated with their presence and how we can reach those management goals. That's all I have. Again, my name is Andy, and if you have any questions, feel free to email me. And I'd like to thank the Joint Fire Science Program, which without I would not be here at the University of Tennessee, and I hope you all enjoyed my presentation. Thank you very much.